Buddy, this is Kurt, and today we're going to be going over some of the foundational material that's related to kinetics. And kinetics is the study of the rate of chemical reactions. And it might seem like very kind of more physicsy than some of the stuff we've done previously, but there's a lot of physics and chemistry, and it actually ties in very much and gives us a lot of information about what's happening in a chemical reaction. Normally we look at a chemical reaction equation and it just has reactants, the little reaction arrow, and then products, and it doesn't give us any information about how do those reactants turn into products. So chemists do kinetics experiments all the time to try and figure that out, and it might not be so clear about how you can figure out what's going on there from the rate of the reaction, but we'll get into that later in the unit. So, what is the rate of a chemical reaction? Okay, so that's a good place to start, and we'll start off with a more, kind of physicsy definition of it. But more broadly, rate is a measure of how quickly a change takes place. Okay, and it's usually related to an amount of time, but it doesn't necessarily have to. So again, going back to something that might be familiar relating to physics is how fast is an object in motion moving, right? That might be something we want to calculate in physics. We throw a baseball, how fast is that baseball moving? So the rate in this case is equal to the change in position, okay? So that delta symbol, that little triangle, it's a Greek letter delta, which means the change in. And so that usually means we're taking some final measure of it minus the initial measure of it. So that'll give us the change. So the change in position, x, okay, x is position and t is time. So change in position over the change in time, and that'll give us the rate. So some common examples, if you've ever driven a car, you would measure how fast that car is going, the rate of that car's motion in terms of miles per hour. If you ever played this video game, I think it's still going on now, but when I was a kid, I played a lot of StarCraft. That video game was really kind of fast paced when you got at the competitive level. And so, how good someone was doing, they'd measure in terms of how many actions per minute were they getting. So, how many times were they clicking and doing something in a given minute? The more actions, usually the better player. The projectile, so that relates back to the more physicsy kind of thing, where we're measuring how many meters maybe is this ball moving in a given second. So let's dive more into that projectile example. So let's say we're taking a ball and we're just throwing it straight upwards. We can measure its height, how high it is, over time, and see how that changes. So here's an example. We've got the height of a ball versus time. So the height is given in meters here on the y-axis. The time is given on the x-axis. And so you can see at first the ball is moving upwards, upwards, upwards. It starts to slow down as gravity starts to get a hold of it, and then it starts to fall back to Earth on the other side. Okay. If we were to just take 2 points, we could calculate the average change, right? Because you can see the rate is actually changing as the time goes on, but we can calculate an average rate, which is a little simpler than finding the rate at any given point. So let's take these 2 points at 0, 0, and after 2 seconds, it's at a height of 12 meters. So if we look at those 2 points, we can calculate the rate using those values. So we need to get the change in position over the change in time. So again, the final position minus the initial position over the final time minus the initial time. And if we plug in those values, right, our final position is 12 meters. Our initial position is 0 meters. Our final time is 2 seconds. Our initial time is 0 seconds. So if we plug those values in, 12 minus 0 over 2 minus 0, we get 12 over 2, and that's 6 meters per second. If we took another 2 points, here we got the point at 2 seconds and at 4. Obviously, the heights have changed now because we're talking about 2 different points in the ball's trajectory. We plug in the values the same way. So we want the change in position over the change in time, final minus initial. And if we plug in those values, our final position was 16, our initial was 12, we get 4. Our change in time is 4 minus 2 is 2. So 4 over 2 gives us 2 meters per second. And it makes sense that it was moving slower because as time goes on, if I throw this ball up as time proceeds, it's going to be moving slower and slower as gravity starts pulling it back to Earth. On the other side, after the ball has reached its maximum height here at 4 seconds, it starts to fall back to Earth. So we can see how that works out. It ends up being a little different. We treat it the same way. So we take our initial and final points. We plug it into our equation here, the change in position over the change in time, final minus initial. But what's different is that our final position is less than our initial position, right? So we get 7 minus 12 meters gives us negative 5 meters, okay? And the time here is just 1 second, right? 7 seconds minus 6 seconds. So we end up with a negative 5 meters per second for our rate. And this makes sense that it would be negative because now the motion is in the opposite direction, right? The ball started off going upwards, but now it's moving in the opposite direction. It's moving downwards, so we give that a negative rate, okay? So we can look at chemical reactions the same way, but we need to have a different metric, right? Because we can't measure a reaction in meters. But what we can do is measure the number of reactions that occur per unit time. And usually the value we use, the units we use to give a number to the number of reactions are represented by the molarity per second for either the reactants or the products. So we focus on one of the reactants or one of the products and see how its concentration changes over time. So for example, we could take this reaction. We've got hydrogen and nitrogen monoxide reacting to form water and nitrogen gas. So we could look at the change. We just focus on one of the reactants here, nitrogen monoxide, and we can see how the concentration of that changes over time. So here's a graph of the concentration of nitrogen monoxide versus time. So these square brackets, if you ever see square brackets, that means the concentration of. So you would read that as the concentration of nitrogen monoxide versus time. And on the y-axis, we've got concentration of NO. On the x-axis, we've got time. And you can see the concentration is going down and down and down and down and down. And that makes sense because this is a reactant, right? So it's getting used up. So we're going to end up with less and less NO because over time it gets used up to form these things on the product side. Great. So let's take 2 points, just like we did with our baseball example. So we've got an initial time of 1 second. Initial concentration of NO is 2.72 molar. We've got our final point here, right? 3 seconds and 1 molar. And so we can plug those into our equation the same way we did with the ball example. But here the rate is not equal to the change in position over change in time. We have to look at the change in concentration of NO over the change in time. But again, we're plugging in these values the same way. The final concentration minus the initial concentration over the final time minus the initial time. When we plug those values in, 1 minus 2.72, 3 minus 1, we end up getting negative 0.860 molarity per second. Okay? Again, makes sense that it's negative because we're losing NO. NO is getting used up. So if we're considering how much NO is there, we have a negative change. We're losing NO. On the other side, though, we could take a look at N2. So this is a graph of the concentration of nitrogen versus time. Concentration of nitrogen's on the y-axis, and again, we have time on the x-axis. And this is increasing now because it's a product. So we're creating N2. So over time, we're going to have more of it. If we look at the same time frame from 1 second to 3 seconds, you can see the concentration has gone up, okay? And if we plug those values in using the same sort of calculation, we end up getting a positive 0.429 molarity per second. So that's the rate of change in the concentration of N2. So again, it should be positive because it's a product and we're making N2. So we're ending up with more of it. So let's compare these two now. So we've got the rate of NO over the time frame of 1 to 3 seconds is negative 0.860. And for N2 during the same time frame, it's positive 0.429 molarity per second. So if you maybe did some quick math in your head, you might have noticed that, wow, the rate of NO is equal to about negative twice the rate of change for N2. Okay? And if I divide those two here, I end up with a relationship of 1 mole of N2 for every 2 moles of NO, right? The rate of change for those two is related that way, which is what their coefficients are in the chemical reaction. And that makes sense, right? Because over that same time frame, from 1 to 3 seconds, however much NO I use up, I must have produced half that amount in N2 because of the stoichiometry here. Okay, and so we can relate all of these reactants and products using this string of equalities, and sometimes this is referred to as the relative rates of reaction. So since each substance is going to have a different rate of change, right? We just saw that. The rate of change for NO was very different from the rate of change for N2. So sometimes we want to have just one value that represents the whole reaction. So we can say the reaction rate is, and we just take -1 divided by the coefficient for each of the reactants, and just 1 divided by the coefficient, right? +1 divided by the coefficient for each of the products, right? Because -1/2 the change in H2 will be equal to -1/2 the change in N2 NO, since they have the same coefficients. And that'll be equal to +1/2 the rate of change for H2O, because it also has the same coefficient, but now it's a product, so it needs to be positive, right? Because the changes will be opposite in sign. And +1/1, or just, it'll be equal to the rate of change for N2, since the coefficient here is 1. Okay, so they all can be related based off of their stoichiometry that way. Now, in the actual example here, we've got nitrogen gas reacting with 3 hydrogen gas molecules, to produce 2 ammonia molecules. So, example problem, or a sample problem that you might have to do, is they'll give you, so the reaction above is carried out in a certain experiment. If the rate of change for H2, okay, is -0.241 molarity per second, what is the rate of change for NH3, the product, during the same time period? So the first step you should always take with any kind of word problem is just to kind of highlight what's given and what's not known. What do we need to figure out? So we're given the rate of change of H2. Delta H2 over delta T is -0.241 molarity per second. What we're trying to find is the rate of change for ammonia. Okay, so we know this. We know that the rate of change for H2 is this value. And we can use the stoichiometry, right? Because it says over the same time period, we can use the stoichiometry just to figure out how much NH3 is going to change by using the mole ratios. So we've got -0.241, and if we write this a little differently, right, molarity is equal to moles over liters. So we could say -0.241 moles of H2 per liter per second is changing. And multiply by negative. Why does it have to be negative? Because NH3 is a product, so we need to end up with a positive value. So -2 moles of NH3 are produced for every 3 moles of H2 that get used up. Okay? So now if we look at it, our units should work out. Our moles of H2 will cancel out, and we'll be left with moles of NH3 per liter per second, or molarity per second, right, in terms of NH3. So we end up here with a positive 0.161 molarity per second. So I want you to just stop for a second and give this question a thought. So here's another example for you to practice on. So I want you to just pause this video and give this problem a shot, and then once you've done it, go ahead and hit play. So I'm only going to pause here for a second because I'm assuming you're pausing. Okay, so hopefully what you did was you looked at what was given and what's unknown, right? Given was the rate of change of CO2, right? So it gave us the rate of change of CO2. over a certain time period. It wants to know the rate of change of O2 over the same time period. So we need to figure that out. We start off with the rate of change of CO2. We have to convert that into how many moles of O2 are being used up over the same time period. So we've got 1.83. We rearrange this and change molarity into moles of CO2 per liter. That way we can use the stoichiometry, right? 7 moles of O2 react for every 3 moles of CO2 that react or that get produced. So if we say negative 7 over 3, 7 moles of O2 per 3 moles of CO2, and again, the negative is there because we're given the value for a product, but we're asked to find the rate of change for a reactant. Okay, and it's going to have the opposite sign, so we need to use a negative sign in here. If instead we were asked to find the rate of change for H2O, since it's also a product, we wouldn't have to put in that negative sign. And if we calculate that out, we get negative 4.27 molarity per second. Okay, and it should, let's see, does that make sense? Well, this is positive because it's a product. Our value is negative because it's a reactant. Great. And it's, roughly double, a little more than double, which makes sense because we're going from 7 moles of O2 to 3 moles of CO2, or vice versa, rather. Okay, so just to recap, what did we go over today? So we went over the reaction rates, how they're measured, right, in terms of concentration versus time. Now, we also could have used atmospheres if we were talking about the gas phase reactions. Sometimes that's used because pressure is actually proportional to the amount of substance in there, okay, if we're talking about gases. So, for example, we're talking about the change in concentration or the change in pressure, let's say, over the change in time. So units of molarity per second is usually what we use. We can calculate the average rate of change for a reactant or a product if we're given the concentration and time information. We can also calculate just the rate of the reaction if we want to have one value that is independent of the reactant or product that we might have studied, right? So that's another thing that we can do, but we also spent a lot of time calculating the rate of change of a reactant or product given the rate of change for a different substance in that reaction. Okay? So I hope that was valuable. We'll get into class tomorrow and we'll go over a lot of this. There's also some other videos that are linked in here, so please give those a view if I was a little confusing, and hopefully that won't be the case going forward. All right, thanks.